Hello everyone, I'm Gauri, and today I will be talking about our paper on end-to-end privacy preserving training and inference for air pollution forecasting with data from rival fleets. Air pollution is one of the biggest concerns faced by developing countries like India and the world at large. Delhi was voted as one of the most polluted capital city in the world for the last decade. In this paper, we focus on air pollution monitoring with respect to forecasting, that is, answering queries about PM values at some future point time based on historical and current values. Air pollution have shown to scale using vehicles instrumented with sensing platforms that generate real-time and historical pollution data. Here, we are interested in learning spatiotemporal models for PM forecasting while preserving location privacy of individual points. Let us now look at the system overview. Fleet vehicles are instrumented with mobile sensors that collect PM data as they roam in the city. However, the data collected by these fleet companies are tagged with location and time, which is sensitive information. This raw data is then aggregated at the respective servers. Now, instead of using only the data streamed at their own server, combining data across multiple servers makes the dataset richer. However, the servers cannot share their collected data directly, as that would reveal the business sensitive information, for example, the spatiotemporal fleet densities. In our solution, we use MPC as a privacy preserving technique to enable joint training of machine learning models. The clients query the model with support of various aggregate queries like average, min, max, etc. Queries are also processed via MPC between the servers and the client. Finally, we consider the setting of two servers and an arbitrary number of clients. We assume that servers are semi-honest and non-colluding during training as well as during inference. The servers learn no information about the model being trained. We also consider malicious clients that might send smartly crafted queries to learn sensitive information about fleet companies. In this case, the query processing needs to first ensure that the query is valid before sending back the result. To solve this problem, we adopt a co-design approach between ML modeling and preserving privacy. The goal is to build efficient ML model systems that preserve privacy with carefully chosen model parameters to balance the trade-offs between ML accuracy, MPC computation, and communication overheads. At every step of our end-to-end system, we carefully balance these trade-offs between privacy, accuracy, and latency. Let us now look at a brief overview of the private training and the querying procedure of our model. Now, given the two server setting and the sensor data collected by the fleet companies, we train our forecasting model in a privacy-preserving manner via 2PC. The two data owners first locally aggregate the sense data. Once the servers have secret share of the grid with PM data, they input these secret shares to a secure two-party computation and get the secret shares of the trained model as output. Since the final output might reveal sensitive information about the data that was used during training, we keep the final model secret shared between the two entities participating in the secure training. Finally, the client queries for an aggregate of subset of these points, which are responded by the two servers jointly, again through MPC. Our system with two data owners can be trivially extended to multiple data owners and two non-colluding servers using standard techniques. Let us now look at the dataset and the training procedure. We use the PM dataset for Delhi NCR that contains PM data recorded over the 3 months from November 2020 to January 2021. The dataset contains more than 12.5 million sensor data points and that spans an area of around 560 square kilometers. The table here shows the aggregate statistics of the PM dataset, PM values in the dataset. It consists of three kinds of pollution, that is PM1, PM2.5, and PM10. Now, we divide the city into small grids of 25 cross 25, each of size around 0.9 square kilometer. Any sensor reading that falls within the boundaries of the grid is binned as an event of that grid. Next, we discretize the time step into buckets of 3-hour duration. Since between 12 a.m. and 6 a.m., the buses are non-operational, we drop the first two buckets from our time series construction. We also explore the inherent patterns or trends in the variation of PM values. The figure here shows the average PM 2.5 values on a single day in the month of December for the points in our trajectories. The lighter colored points indicate lesser pollution values, while the darker colored points indicate higher values. As we can see, spatial patterns in PM values are evident from this plot that nearby locations are similar in color. Next, we also explore the temporal patterns in the data. The figure here shows average PM 2.5 distribution within a day, and that it has higher PM values at night and lowest around 3 PM every day. The second figure also shows the PM 2.5 distribution across the long period of 3 months. As we can see, there are no defined long-term patterns in the dataset. Forecasting PM values for later in the longer future seems not trivial. Hence, we do not explore the long-term forecasting in this work, but focus on short-term forecasting for the next 3-hour windows for a day. We use the GCN LSTM spatiotemporal model for forecasting Delhi pollution data. The model consists of multiple GCN layers stacked over multiple LSTM layers. While the GCN is used to capture the topological structure of the network for obtaining spatial features, the LSTM units capture the temporal features. We also perform experiment with varying number of units in both the GCN and LSTM layers. The table shows that the GCN LSTM architecture with 2 GCN layers with 4 size 4 units in each and 1 LSTM layer with 4 units give the best test RMSE results on the data. This small model not only gives the best RMSE values, but also low computations overhead in the private training. We further make smart design choices for the model architecture. We study the parameter sequence length, which is the size of the past window of information to be used for LSTM modeling. Now, using the autocorrelation function, we identify which lags have significant correlations and understand the patterns and properties of the time series. These correlations indicate that the past values influence the current value. The figure shows that lag 6 has large positive correlations and that the correlations taper off as the lags increases. This means that observations YT and YT minus 6 are highly correlated, and hence we choose the sequence length equal to 6 as a modeling parameter for time series. Now, since the problem of forecasting is based on incoming streams of time series data, we evaluate 2 training procedures for training our model on new incoming streams. One is training from scratch. In this, as we have a new stream of training data for the next day, we train the model again from scratch with randomly initialized model weights. In the other one, that is the fine-tuning, instead of randomly initializing the model weights, we fine-tune the previously learned model weights with a lower learning rate as and when we receive new streams of pollution data. We compare these 2 training procedures, and as it is evident from the figure, the training from fine-tuning as compared to the training from scratch converges much faster and smoothly. We also present the evaluation of our GCN LSTM model with the above defined model parameters and the 2 baselines, ARIMA and NBeats, on different test days as shown in this table. So we can see that our construction of the GCN LSTM model on the Delhi PM pollution dataset outperforms on both of these baselines. Let us now briefly look at the summary of our method. The secure training of the GCN LSTM was implemented using the state-of-the-art MPC framework with the SecFloat backend. The SecFloat provides privacy guarantees in 2PC, which are up to 2 orders of magnitude more efficient and up to 6 orders of magnitude more precise than prior cryptographic libraries. The fine-tuning of the model was carried out for 20 epochs with a runtime of around 1.6 hours to predict the PM values for the next 3-hour window. Latency versus accuracy trade-offs were analyzed at each step of the model training. We achieve these training time and latency with a careful choice of machine learning model parameters, as we talked in the talk before, like architecture, number of layers, sequence length, grid size, time units, and the history and different training procedures like training from scratch versus fine tune. We thus show it is indeed practical to train useful machine learning models on contiguous streams of training streaming data in a secure manner if the model parameters are chosen carefully to balance machine learning accuracy and MPC computation and communication overheads. Thank you.